Okay, so this is part two to section 7.1. We're still talking about integration by parts. So we have a um, brand new method of solving these integrals that's not U substitution and it's not just finding an antiderivative. So I wanted to kind of look at the last example we did. So we had integral x sine of x dx, and we went through and we did this, and we were able to find that using integration by parts, this was minus x cosine of x plus sine of x plus your arbitrary integration constant, because it's an indefinite integral. So the question is, so at the beginning I set u equal to x and dv equal to sine of x dx. So the point of integration by parts is I get to pick u and I get to pick dv here. And whatever you pick for dv has to include the dx, just kind of a rule, because it's a differential. So the question is, why did I pick x and to be u, and why did I pick dv to be sine of x? So what you'll notice is when I do integration by parts, I'm going to differentiate something. I'm going to find the differential of u, and I'm also going to integrate whatever dv is to get v. So the reason this worked out, and the reason this worked nicely when I picked u to be x, is that when I picked u to be x, it got rid of x. I took a derivative of x and I was just left with dx. Whereas if I'd picked, if I'd instead picked x to be dv, I would have had to integrate that. And the integral of x is x squared over 2. And when you do that, you're going to get something more complicated. So the point of integration by parts, and one of the times it is really, really useful, is if you have like an x sitting out here and you're trying to get rid, and you want to get rid of it. So you do integration by parts to eventually just be left with a dx. And you might have to do integration by parts more than once. We'll see an example here where I have to do integration by parts multiple times. So just as kind of a rule of thumb, for these kinds of integrals where you have x times another function or an x squared times another function, typically u is going to be whatever you can differentiate to eventually get rid of, to just get a dx at some point. So let's see an example, and this example is not going to include that. So we have the integral of the natural log of x dx. So you'll look at this one, and again, you'll try and go through, okay, what do I differentiate to get natural log? I don't know. Is it a u substitution? There might be a clever choice of u that'll work, but we're not going to do this one by u substitution. So just as kind of a note, u substitution you can actually always do if you already know the antiderivative. So it's kind of cheating. So we're going to pretend like we don't know, or that we're not going to do u substitution on this. So let's try and do integration by parts. So we need to pick a u and we need to pick a dv. So when I'm picking u and dv, again, I need to pick things that I can differentiate and integrate. So I'm not going to pick ln of x to be dv. So I'm going to have to integrate that. And I'm trying to find that integral. So that just seems kind of pointless to do that. So we're going to pick u to be ln of x. Then dv is everything that's left over, and it's just that dx there. So I'm going to, so now I'm going to figure out what du and v are. So if u is ln of x, du is the derivative, 1 over x, times dx. And if dv is equal to dx, if I integrate that, I'm just going to get v is equal to x. So now I'm going to use my formula. Integral u dv is uv minus integral v du. So this integral here is u times v, so it's x times ln of x, minus the integral v du. So v is x, du is 1 over x dx. And you'll see why this actually worked out really nicely. So this is x ln of x minus the integral x divided by x is 1. So I'm just left with the integral dx here. So if I continue here, I'm going to get x, sorry, this is a minus sign, not a multiplication sign. If I continue here, I'm going to get x ln of x minus, and the integral dx is just x. And of course, an arbitrary integration constant there. So you'll see here that the reason why this one worked, and in this case, is because when I did integration by parts, the integral I was left with was something that was doable. This one's a little harder to see that you need to do integration by parts with, But if it's not, so at this point, if it's not U substitution, and it's not something that you can just write down an antiderivative for, then it's going to be integration by parts. Okay, so let's do an example, and I'm trying to keep these videos shorter, but these are, so this is a little harder to do because this example is going to take a minute, but I'm going to go ahead and do this one. So we have the integral t squared e to the t dt. And again, I look at this and I automatically know that this is integration by parts, because if I differentiate this, 3 times, sorry, 2 times, 2 times, I'm going to get, something that just is, a dt there. So the thing that tips me off to that this is integration by parts is I have something that'll disappear if I integrate a bunch of times, and then something that won't, but something that I know how to integrate. So we're going to do integration by parts here. So we need to pick u and we need to pick dv. Well, remember that, u is the thing I'm going to take the derivative of. So I'm going to take the derivative of the thing that's eventually going to disappear. And dv is going to be all the stuff that's left over. E to the t dt. So now I can compute du and I can compute v. So du then is just the derivative 2t times dt. So I need differentials. And then if I integrate this and get v, I'm just going to be left with e to the t again. So now integral, so again, just keep writing this down until it sticks in your head. Integral u dv is uv minus integral v du. You can also remember, these are the way the arrows go, uv minus v du. You're going to ignore the dv, you don't do anything with that in the integration by parts formula. So then that tells us that the integral t squared e to the t dt is going to be equal to uv, so t squared e to the t minus the integral, and then I have v du. So I'm going to get 2t e to the t dt. And what you'll notice is I still cannot integrate this. Still can't integrate this function here. Not directly. I can't just think up an antiderivative for that. So that tells me I have to do integration by parts one more time. One more time because, I'm trying to get rid of this t here. Because as soon as this t is gone, I can integrate e to the t. So I'm going to do integration by parts once more. And I'm not going to change the letters that I use for my variables because it's harder to remember these things if you do. So I'm going to pick u and dv again, where I'm only looking at, this integral here. So u in this case, I'm going to pick it to be 2t. And then dv is going to be everything that's left over, e to the t dt. And I figure out du, and I figure out v. Du then is just this derivative, which is 2 times dt. V is the center, to find v, I take the integral, and I get e to the t. And now I just continue. So I get t squared e to the t minus, and I'm going to subtract off all of this. Let me clean this up. So e to the t up there. All right, so now this integral, 2t e to the t, is going to be uv. So I'm going to get 2t e to the t minus the integral v du. Integral v du is now 2 e to the t dt. And now you can see if I factor this 2 out, this integral I can now do. And that was the whole point of this integration by parts. We're trying to reduce this down to an integral that we're actually able to do. So this is t squared e to the t minus 2t e to the t plus 2 times the integral e to the t dt. And just continuing, we can do that last integral now. T squared e to the t minus 2t e to the t. This integral is 2 e to the t. And don't forget your arbitrary integration constant. And that would be, this integral here. Okay. Just making sure I haven't screwed up anywhere. Okay, so this is going to be where I'm going to stop this video. You know, this is so integration by parts is super useful. I use it all the time. My background is actually in physics, and I don't know if anybody else is really interested in physics. I think most people are engineers, but if you ever do a course on quantum mechanics or physical chemistry, these types of integrals show up all the time. These t squareds, e to the t's, very common integrals. So it's important to know how to do this. So I'm going to stop here. We'll do a couple more examples, talk about how to do the definite integral, and continue from there.